Welcome to lecture on Introduction to Nonlinear Programming Problem. Now, first of all, what is operation research? Operation research is basically a scientific technique which provides us with a quantitative basis to take optimal decision in various business problems or planning problems. Now, let's recall what linear programming problem is. A linear programming problem has three components: objective function, which is either a maximization function or a minimization function, and there are certain set of constraints or restrictions on the availability of the decision variables. They are given in terms of inequalities or equations. And third part is the non-negativity restriction. So it is assumed in a linear programming problem, the objective function and the constraint inequalities, they are linear functions of the decision variables. Now, to find the solution of linear programming problem, we look for the optimal solution at the extreme points of the feasible region. Now, what is feasible region? Feasible region is the solution space of the given problem where all the constraints and the non-negativity restriction are satisfied. So, therefore, we look for such an extreme point where the objective function has optimal value. So in case we have two decision variables, then we can take the help of graphical method. Otherwise, if we have two variables or more than two decision variables, then we can use simplex algorithm and the variants of simplex algorithm, which are Begin method and two-phase methods. Now coming to nonlinear programming problem. So nonlinear programming problem usually refer to the problem where the objective function become nonlinear or sum of the constraint inequalities hold nonlinear relationship, or both of these are nonlinear. So a nonlinear programming problem can be unconstrained type or can be constrained type. So an unconstrained single variable nonlinear programming problem has the form optimize z is equal to f of x, where f of x is nonlinear function of the single variable x. And the search for the optimum value of x is conducted over the entire interval minus infinity to infinity. Now, if our search is restricted to a finite subinterval AB, then the problem becomes optimize z is equal to f of x subject to x lying between A and B. Then it is a one variable constraint problem. The general form of nonlinear programming problem is to determine the n tuple x is equal to x1, x2, so on up to xn, so as to optimize z is equal to f of x, which is subjected to the constraints gi of x1, x2, so on up to xn, less than equal to or greater than equal to bi, I varying from 1 to m, and xj greater than equal to 0, j varying from 1 to n. So here f of x or sum of gi of x or both are nonlinear functions of the decision variables. Now let's try to understand the solution of a nonlinear programming problem, of various nonlinear programming problems with the help of this flowchart. So nonlinear programming problem is broadly divided into two parts, unconstrained and constraints. In case of unconstrained problem, it may be a single variable problem or it may be a multivariable problem. So if it is a single variable problem, it can be solved using the help of local and global optima. And if it is a multivariable problem, it can be solved using gradient vector and Hessian matrix. In case of constrained nonlinear programming problem, if we can again have two choices, either the constraints are equality constraints or the constraints are inequality constraints. So if the constraints are equality constraints, it can be solved with the help of Lagrange's multiplier method. And if we have a non-linear programming problem with inequality constraints, then it can be solved using Tucker condition. So the solution of a non-linear programming, unlike linear programming problem where the optimal solution lies at the extreme points, the solution of a non-linear programming problem can also lie at the boundaries or even the inside the feasible region. So it is not necessary that we'll get the optimal solution of a non-linear programming problem at the extreme points only. The solution can lie at the boundaries also, or it can even lie within the feasible region also. So for different type of non-linear programming problems, researchers have developed different algorithms. So there is no particular solution for there is no general solution for all nonlinear programming problems. For different nonlinear programming problems, we have different algorithms to solve them. Now first come to local and global optima. An objective function f of x has local minima at x naught if there exists a small interval centered at x naught such that f of x is greater than equal to f of x naught for all x in this interval at which the function is defined. And if f of x is greater than equal to f of x naught for all x at which the function is defined, then the minimum at x naught is a global minimum. So local and global maxima are defined similarly, only the inequalities are reversed. So let's try to understand this with the help of the diagram. Here in the diagram you can see if I take the interval a to x1, then the then the value of function at any point in the interval is greater than equal to the value of function at point A. Therefore, the local minima uh, of this function is in this particular interval a to x1 is A. If I take the interval from x1 to x3 suppose, then the minimum value of the function occurs at the point x2. So that means x2 is the local minima for the function f of x in the interval x1 to x3. But if I take the entire interval from a to b, then the value of the function is minimum at the point x2. That means this x2 is the global minima of the function. Similarly, we can say that the global maxima occurs at the point B. Now, there are certain results from calculus which are useful in finding the local and global optima. So, if f of x is continuous on closed and bounded interval AB, then f of x has global optima on this interval. If f of x has local optima at x naught, and if f of x is differentiable on a small interval centered at x naught, then f dash of x naught is equal to 0. And third result is if f of x is twice differentiable on a small interval centered at x naught, and if f dash of x naught is equal to 0 and f double dash of x naught is greater than 0, then fx has a local minima at x naught. So for what is the condition for the minima? That for the local minima, that f dash x naught is equal to 0, and whatever value whatever point that we'll get from here, x naught, whatever value of x naught that we'll get from here, if we calculate the second derivative of f at this point x naught, that should be greater than 0. Similarly, if we have f dash at x naught is equal to 0 and f double dash at x naught is less than 0, then f of x has a local maxima at x naught. So a function f of x is convex on an interval S, which may be finite or infinite, if for any 2 points x1 and x2 in S, and for all a lying between 0 and 1, if f of ax1 plus 1 minus a into x2 is less than equal to a into f of x1 plus 1 minus a into f of x2. So then we say that the function f of x is convex function. So if one holds with the inequality reverse, then f of x is concave. The negative of a convex function is concave and conversely. So convex functions and concave functions are unimodal. Now, there are two results related to these convex function. If f of x is twice differentiable on S, then f of x is concave on S if and only if f double dash x is greater than equal to 0 for all x in S. It is concave if and only if f double dash x is less than equal to 0 for all x in S. Second result, if f of x is convex on S, then any local minima on S is global minima on S. If f of x is concave on S, then any local maxima on S is global maxima on S. So that is why these functions, convex functions, are important in the solution of nonlinear programming problem, because if we are able to find a point of minima and we have verified that the given objective function and the functions in constraint inequalities, they are convex functions or concave functions, then any point of minima will be the global minima, or any point of maxima will be the global maxima. A multivariable unconstrained nonlinear programming problem has the form optimize z is equal to f of x. So as I told you earlier also while we were discussing the flow chart, that in case of a multivariable unconstrained problem, we take the help of gradient vector and Hessian matrix. So let's recall what gradient vector is and what Hessian matrix is. So the gradient vector del of f associated with the function f of x1, x2 so on up to xn, having first partial derivatives, is given by del of f is equal to curl f by curl x1, curl f by curl x2, so on up to curl f by curl xn. The notation del f of at the point x naught signify the value of the gradient at x naught. So let's find out the gradient vector in this example. Here f of x1, x2, x3 is given as 3x1 square x2 minus x2 square into x3 cube with x0 1, 2, 3, and we have to find the value of del of f at x0. So del of f will be a vector whose first element is curl f by curl x1. So that is 6x1 x2. Second element will be curl f by curl x2, which is 3x1 square minus 2x2 x3 cube. And third element will be curl f by curl x3, which is minus 3x2 square x3 square. So if we evaluate this del of f at the point x0, means putting the value of x1 as 1, x2 as 2 and x3 as 3, we'll get the value 12 minus 105 minus 108. So now come to the Hessian matrix. The Hessian matrix associated with the function f of x1, x2 so on up to xn that has second partial derivatives is given by we denote it by h, or h of f means the Hessian matrix of the function f, and it consists of all the second derivatives of f with respect to the xi I varying from 1 to n. So Hessian matrix for the example that was given on the previous slide is given by this. So here the first element of the matrix is, since we have three variables, so we'll get a 3 by 3 matrix. The first element of this matrix means the element in the first row will be curl to f by curl x1 square, which is 6x2. The second element in the first row will be curl to f by curl x1 curl x2, and the third will be curl to f by curl x1 curl x2 curl x3. So similarly, we can find all the elements of this Hessian matrix. Now, how to find the optimal solution using this gradient vector and Hessian matrix. So there are some important results which will help us to find out the solution using these solution of this multivariable optimization problem using these gradient vector and Hessian matrix. So a necessary condition for a continuous function f of x with continuous first and second partial derivatives to have an extreme point at x naught is that each first partial derivative of f of x evaluated at x naught vanish. That is, del of f at x naught is equal to 0, where del of f is the gradient vector. So this condition is satisfied for cases other than the extreme points. These include inflection points or saddle points. So therefore, the above condition is not sufficient for determining the extreme points. The points obtained from the solution del of f is equal to 0 are called the stationary points. So whatever points that we'll get after finding this del of f at equal to 0 are called the stationary points. The sufficient condition for a stationary point x naught to be an extreme point is that the Hessian matrix H evaluated at x naught is negative definite when x naught is a maximum point and positive definite when x naught is a minimum point. So to recall, if delta I are the principal minors of the matrix H, then a matrix H is positive definite if and only if delta I are strictly greater than 0, and positive semi-definite if and only if the principal minors are greater than equal to 0. And the matrix H is negative definite if and only if delta 1 is less than 0, delta 2 is greater than 0, so on up to minus 1 raised to the power n delta n greater than 0. And negative semi-definite if and only if delta 1 less than 0, delta 2 greater than equal to 0, and so on up to minus 1 raised to the power n delta n greater than equal to 0. So using these principal minors and their sign, we can find out whether the given matrix is negative definite or positive definite. So, and once we have found the whether the matrix is negative definite or positive definite, then we can check the value of the then we can say that the point at which we have found the stationary point at which we have found the value of the matrix is a maximum point or a minimum point. So this will be more clear with the help of example. For each of the following functions, determine whether it is convex, concave or neither. F of x is equal to 10 minus x square. So this is a one variable problem. So what we'll do, we'll find out first derivative and put it equal to 0. Then we'll get the point x is equal to 0. Now finding curl to f by curl x square at this point x is equal to 0, we find that it is minus 2, which is always less than 0. So that means f is concave and x is equal to 0 is the point of maxima. So similarly we can do the B and C part. Now we take the E part, which is a multivariable unconstrained optimization. So we have to check whether this function is um, convex or concave. So here we'll evaluate the Hessian matrix. Hessian matrix is the matrix of second partial derivatives. And once we have found the Hessian matrix, then we'll evaluate the first principal minor is 4. So that is greater than 0. And then we'll evaluate the second principal minor. Second principal minor is what? Determinant 4 minus 2 minus 2, 2, which will come out to be 4, which is greater than 0. Therefore, since both the principal minors are greater than 0, therefore the function is, this matrix is positive definite and the function is strictly convex function. So in the similar way, you can solve the rest of the questions. Now, apart from constrained and unconstrained nonlinear optimization problems, we have following types of special NLPPs. So one is quadratic programming problem. In this, we have the objective function in quadratic programming problem is in quadratic form. means every term in the objective function is of degree 2. So, and the constraints are linear. So if we have this kind of nonlinear programming problem where the objective function is in quadratic form and the constraints are linear inequalities, then we say that it is a quadratic programming problem, and we have a special algorithm to solve these kinds of nonlinear programming problem. And next is separable programming problems. Separable programming problems, in this, if the objective function is in the separable form, means it can be separated into functions of the different decision variables. Like if I have x1 f of x is equal to x1 square plus x2 square plus 3x1, then I can separate it as a function of x1 and plus a function of x2. So if the objective function is in this form, then it can be solved using separable programming problem. So next is convex programming problem. In convex programming problem, um, if we are able to verify the convexity or concavity of the objective function and the and the inequalities functions in the inequalities, then we can say that this programming problem is a convex programming problem. So in a convex programming problem, if the constraints or the objective function are either convex or concave, then we say that it is a convex programming problem. And whatever solution that we will find in the optimal solution we'll find will give us the global optimal solution. And in case of non-convex programming problem, means if we are not able to um, verify the convexity or concavity of the objective functions or the functions in the constraint inequalities, then the solution optimal solution found in these types of nonlinear programming problems will be a local optimal solution. So that is